Okay, let's look at experiment 4, which is about DC power supplies. So before we go on to understand how a DC power supply works and what circuits it contains, we first have to understand the fundamental circuit element that goes into making a DC power supply, and that is called a diode. Without going into the history of diodes, we used to have diodes 50 years ago, 60 years ago that were about 5 centimeters in size and about an inch in diameter, about 2 centimeters in diameter. Let us talk about the modern diode, and they do come in all shapes and sizes. We will speak about diodes which are normally used for circuit experiments in the laboratory, which can support about half an ampere of forward current and can be used for a lot of applications. So the first thing to understand is what is special about a diode as a circuit element. For example, what is the difference between a diode and a resistor? So let's look at this. A diode is a resistor in a sense whose resistance depends upon the polarity of the voltage you apply upon it. Thus, if you apply a voltage across the diode in what is called the forward direction, then the resistance is nearly zero. And when you apply a voltage in the reverse direction, the resistance is nearly infinity. For an ideal diode, of course, we say that the forward resistance is indeed zero and the reverse resistance is nearly infinity. So let us plot the characteristic of the diode with respect to voltage and current. It would look like this. This is the voltage axis, this is the current axis, and as I said, when you apply a forward voltage, that is to say when the applied voltage is positive, then the current, it acts as a short circuit, so there is any amount of current can flow through the diode without giving rise to a voltage drop across it. So you would have a characteristic like this. And when you apply a reverse voltage, then absolutely no current flows because it acts as a very high resistance. So you would have a characteristic like this. So this is an ideal diode. No practical diode that's made with electric circuits is ever going to be ideal. But it tries to be ideal in a major part of its characteristic. Superposed on this, I will draw the characteristic of a non-ideal diode, of a practical diode. A practical diode does have a small amount of current even when applied, even when a reverse bias is applied, even a reverse voltage is applied. And that in fact flows until a very large reverse voltage is applied, when the diode breaks down and allows a lot of reverse current. But that happens only once in its lifetime for the last part of its life. So we are never supposed to apply a very large reverse voltage to the diode. Whatever voltage we apply should be within what is called the peak inverse voltage rating of the diode. So let's look at the reverse characteristic first. Something of this kind. Until it breaks down. And the breakdown phenomenon would look like this. So you see, when reverse voltages are applied, there is a very minor current. In fact, the graph which we are drawing makes no claim to be proportionate. It's only indicative. The reverse currents are of the orders of nanoamps or microamperes, whereas the forward currents are easily in the order of milliamperes, maybe even amperes. So this is up to this point. Now, when a forward voltage is applied, the non-ideal or practical diode does the following. Until about half a volt is applied in the forward direction, it still hesitates to conduct a current. When voltages greater than half a volt are applied, it starts conducting wholeheartedly. So, on the positive side, the curve goes like this. Very clearly, you can observe two things about the forward behavior. One, that there is a so-called knee voltage or cut-in voltage of around 0.6 or 0.7 volts. You might even observe 0.8 volts in the laboratory, and it's called, as I said, a knee voltage. Technically called a cut-in voltage. And that is this. Of the order of 8 volts, 0.6 to 0.8 volts for a silicon diode. Right? Now, after it has cut in and after it starts conducting current, it still has a non-zero forward resistance, so that this part of the curve really doesn't have a vertical direction. It has a slightly slanted characteristic, as you can see, and this slant indicates that there is a very, very slight resistance, maybe of the order of a few ohms, and this slope, or rather the inverse of this slope, indicates this slope indicates the inverse of the resistance. That is, this is a very large slope on this graph, so it represents a very small resistance. So this is the entire behavior of the diode. Now, what you will do in the laboratory is to rig up a circuit which will plot this characteristic on your digital oscilloscope. For this, you need to measure two things. Clearly, you need to know the voltage, you need to know the current at the same time. Now, the oscilloscope, as you already know, can measure current and can measure voltage, but it cannot measure current. So the only way you can make the oscilloscope measure current is to convert that current into a voltage by including a small resistor in series with the diode and measuring the voltage across that resistance. However, there are problems associated with measuring the current in this manner, which we will now discuss. So here is the circuit we use to carry out the experiment that determines the characteristic of the actual diode. Here is the actual diode under test in this place, and here is the resistor that I said you need to connect in series to measure the current that flows through the diode. Now clearly what we want to do is to measure the voltage across this resistor and recognize that being a linear resistor, the voltage is indicative, though not numerically equal, to the current of the diode and the resistor, which are in series. So what the voltage will tell us is a number which is proportional to the current through the diode. At the same time, on channel 1 over here, we can measure the actual voltage between the diode and the ground. This part is grounded because this is the function generator source which produces a supply which is also grounded at one end, and this oscilloscope also makes measurements only of voltages which are with respect to the ground. And this is an important point. Why are we putting this thing DA over here? The DA stands for Difference Amplifier. The difference amplifier is a circuit which accepts two floating voltages, let's say V1 and V2. V1, V2 are two voltages in a circuit, Neither of them is a ground voltage. Both these values are with respect to the ground, and on accepting these two inputs, V1 and let's say V2, the difference amplifier produces V2 minus V1 with respect to ground. It produces a single voltage which is measured with respect to ground. This is the task that needs to be done, because for either channel of the oscilloscope, one end of the two terminals of that channel is already grounded. So if we take these two wires and connect them to one channel of the oscilloscope, for example, if I connect this and this, then the oscilloscope will itself ground this point. So there will be no voltage across the diode at all. Hence, an oscilloscope can measure only voltages with respect to ground. It cannot measure a floating voltage, which is what you will find across this resistor. So, floating voltage across the resistor is converted by the difference amplifier into a grounded voltage, goes to channel 2. The diode voltage here goes to channel 1. There is in fact a means of measuring a floating voltage even with an oscilloscope, and the right way to do that would be to connect this to one channel of the oscilloscope and this to the second channel of the oscilloscope, and then use arithmetic features of the oscilloscope to subtract channel 2 from channel 1 and plot that waveform, which is the subtraction of these two quantities, of these two functions. That is possible, but if we did that, just the measurement of the current or the voltage proportional to the current would consume both the channels, and we would require a third channel, which means a new scope altogether, because this scope has only two channels, to measure the voltage of the diode. Thus, to save on oscilloscopes, we use a difference amplifier, and the difference amplifier gives you an output proportional to the current. To work out the constant of proportionality, look at this resistor. This resistor we have used is 1 kilo ohm. So if it gives you 1 volt here, that means the current is 1 milliampere. If it is n volts, it is n milliamperes. So you can read off channel 2 in milliamperes. Channel 1 is read out in volts. Now if you put this oscilloscope in XY mode, something that you have already done in previous experiments, you would see a plot after going through all the procedures of centering the dot and the screen, etc. You would see a plot that looks like this on your scope. This is what you would see. You would not see this part because, as I said, that is a destructive process on the diode. You do not want to see that. It happens only once. And this is being done repeatedly because a sawtooth waveform is being applied to this circuit and it is generating this. So you cannot see the breakdown. You can only see the part before the peak inverse voltage, which is here, this part, and you can see the forward part. Now it's already been explained, it's going to be explained to you that you take a tangent of this curve over here, see where it meets the V axis, and that gives you the cut-in voltage, V gamma. All that will be explained to you by the people who carry out the experiment. Now, having done all this for an ordinary diode, we use the same setup to observe what is called a Zener diode. A Zener diode, as far as its normal diode characteristics are concerned, that is the forward behavior and a major part of the reverse behavior, is just like an ordinary diode. There is not much difference. Where it differs, however, is that it allows for a non-destructive breakdown under large inverse voltages. And that breakdown phenomenon is called a Zener breakdown. The Zener breakdown is a repeatable phenomenon. You can Zener break down a reverse Zener diode any number of times. And one of the very nice features that broken down Zener diode possesses is a very, very constant voltage irrespective of current under breakdown conditions. In short, its incremental resistance under breakdown is very, very small. Let me plot a Zener diode's characteristic for you. Not necessarily to scale, but indicative. This is the forward characteristic, a small reverse saturation current, and then a nearly vertical line. Now, if you replace this diode in the circuit by a Zener diode, whose symbol is this, and apply a signal here of sufficient amplitude to cross the Zener breakdown voltage Vz, then your screen would actually see show you something like this. You would see the breakdown region as well, which you could not have seen with the ordinary diode. You would see this forward part, the reverse unbroken down part, and the broken down part. You can even try to take the inverse of this slope and estimate the reverse resistance of the Zener under breakdown conditions. But the value will be so small that I doubt you will be able to get a very accurate figure. Initially it's slightly curved over here, but then it becomes literally straight. That doesn't mean that this curve goes on forever. There is a maximum current. This is the current axis after all, and there is a maximum current beyond which, if you drive this in a diode, it would just burn out. It would overheat and burn out. So we don't want to do that. We want to just look at the characteristic of the Zener and plot its characteristic as we have done. Compare this characteristic with the ordinary diode's characteristic without the breakdown part of the curve. So this much is part 1 of.
Welcome to experiment number 3. The main aim of the experiment is to study the IV characteristics of diodes. The two diodes are Zener diode and general diode. In this experiment, we are going to study about the new component called differential amplifier. The differential amplifier circuit is already made on a printed circuit board with P and Q as its input and R as its output. As you can see, this is the PCB, printed circuit board. This is the differential amplifier. In this, Q and P are two inputs and R is the output. And the power supplies, DC power supplies are given across these wires, 12 volts, minus 12 volts and ground. If you give two inputs to Q and P, the outputs will be the difference of voltages across Q and P. So it is given in the manual that VR is equal to VQ minus VP. So you should not forget connecting the plus 12 volts, minus 12 volts and ground connections in the PCB. Now we will tell about the different circuit elements like diode, capacitor, resistance, Zener diode, how to identify the terminals of these elements. Now we will start with the diode. This is the ordinary diode. The number of the diode is written on this device, the diode, and these are the two terminals of this device. This silver ring indicates the cathode of the diode. So this green color wire is connected to the cathode of the diode, and the red one is connected on the other side to anode. It means this is the actual diode symbol. So in the circuit, this arrow indicates anode, this one indicates cathode. So the silver ring is the cathode one. This is the way we have to connect the diode. This is the normal one. And we will tell about Zener diode. Now this is the Zener diode. For Zener diode also, the negative band that is in this side, on the side that is gold, indicates the cathode, and the other side indicates the anode of the Zener diode. So this is is the way we have to connect in the circuit. Now we will tell about the capacitors. This is different type of capacitor, not the ceramic type. This is the electrolytic capacitor. So now this black streak, this indicates that the terminal close to it, that is this is the short wire, this acts as the negative terminal. The other side, which is this one, where there is no negative streak, it acts as a positive one. So this is electrolytic one, that is polarized one. So when we are connecting this capacitor in the circuit, we have to be careful. We should correctly connect the circuit. This is different type of capacitor. The capacitor ratings are written on the capacitor here. Similarly, this is the another type of capacitor, 1000 microfarads. Rating is given. Now we will show you the wire wound resistors. This is not the ordinary carbon resistors. This is the wire wound resistors. Here the rating is indicated that this is of 1 ohm resistor. 1E means 1 ohm, plus or minus 5% is the tolerance one. This indicates the power rating. Normal resistors with the same value cannot withstand in high power circuits. So when current is high, then we have to use this type of resistors as loads, so that we can prevent the resistor from getting damaged. This is the wire wound resistor, and this is the wire wound resistor but different value. 100E indicates 100 ohms. Now this is the step down transformer. The input of it is 240 volts and the output of it is 12 volts. We can switch it on using this one, and this is the tapped terminal. From these two we get the in phase sinusoidal signal of peak value 12 volts. This is the out of phase one. From this we will get 12 volts peak to peak out of phase sinusoidal signal.
Coming to the first part of the experiment, that is observing the IV characteristics of a diode. First, coming to the interconnections, that we will give inputs of plus 12 volts and minus 12 volts from the DC power supply. So first making on the DC power supply and keeping plus 12 volts and minus 12 volts by giving, as you can see the interconnections there, by varying the coarse and fine knobs on the green part. You can keep plus 12 volts and minus 12 volts. The red wire indicates the plus 12 volts and the black wire indicates the minus 12 volts and the green wire indicates the common ground. You can see these variations by pressing the plus S2 and minus S2 knobs there or switches there. And we can make the variations by using the coarse and fine by setting the plus 12 and minus 12 volts. So we will give the inputs to the differential amplifiers. So coming to the experimental part, that is we should apply 8 volts peak triangular wave, which is having a frequency of 200 Hz. So by coming to the frequency generated part and giving 200 Hz frequency, and by using the wave button, keep in triangle, so you will get a triangle. So we give input. And making variations in amplitude, we can give 8 volts peak to peak. So 16 volts peak to peak. So by making on the DSO, we can the interactions are done according to the diagram that is given. As you can see, the Q input is given across the supply, across the resistor, and P input is given across the diode. So differential output will be the difference of both Q and P. So by keeping XY mode, we can observe the IV characteristics. So now to observe the IV characteristics, first we should make on the DSP. So So we can observe these are the two output waveforms of both channel 1 and channel 2. So we should observe IV characteristic along XY mode. To observe waveforms in XY mode, so first we should keep the dot across the center. So we can verify this by keeping in both channel 1 and channel 2 in ground modes. By using menu button, keep in XY mode. As you can see, there is a dot, and keep it exactly center so that we can observe the IV characteristics. Yes, now it is in exactly center. Now press again channel 1. Make the waveform. So by this you can observe the IV characteristics of a diode. So we can verify that we are getting the correct diode characteristics. So next part we have to estimate the new voltage V gamma of the diode. So by observing the waveform here, we can observe the V gamma by using this voltage per division and across the channel 1. We can easily get the new voltage. For this part, we should keep channel 2 voltage setting as 0.5 volts per division or 0.2 volts per division. By that we can easily observe the new voltage. Next part is we have to draw all these characteristics, diode characteristics, and note down all the salient points. The final step of this experiment is to find the diode forward resistance by measuring the slope of the conductive region. So in this linear region, we should take two V points and I points, and finding the slope of both V and I, we will find the diode characteristics, diode forward resistance. So by completing this, the first part is the IV characteristics of the diode are completed. So the next diode that we are going to discuss is Zener Diode. We are going to observe the IV characteristics of Zener Diode. The circuit interconnections are all same as considered in the previous case. The only change is replace the general diode with the Zener Diode. As you can see, these are the characteristics of Zener Diode. The Zener Diode in the forward bias case or in the first quadrant, it will act as similarly as general diode. So we should in the reverse bias case, so it will have a breakdown voltage where suddenly the reverse saturation current will increase. So repeat all the steps that we have done previously, and the last step, along with finding the new voltage, we should find the Zener breakdown voltage. As you can see that the Zener breakdown voltage is shown in the diagram in the manual, that is pitch inverse voltage. We have to draw a linear tangent line along that line, along the slope line, and that voltage point as the x-axis voltage and y-axis current, that voltage will tell about the Zener breakdown voltage. Similarly, to find the forward new voltage as said in the previous case, draw a tangent along the forward axis line, forward characteristics, and the point that is touching on the x-axis will give the forward new voltage. So by doing this, the Zener part is completed.
So the second part of the experiment consists of building a rectifier. What is a rectifier? A rectifier is a circuit that converts alternating voltages, that is voltages which go both positive and negative with respect to the other terminal, into a voltage which always has the same polarity, though not necessarily the same magnitude. Let's take an example. If you take a sinusoidal voltage, then its waveform would be like this. What we are saying here is that if at any instant of time like this one, you measure the voltage is a number. And what does this represent? You have somewhere 2 points on the circuit. Let's call this A and B. And and let's say that this voltage is VAB. This of course is the time axis. What we mean by saying VAB has this shape is to say that at this point of time, VA, the voltage of point A with respect to B, is so many volts, let's say 10 volts. But if you measure the same voltage of the same terminal A with respect to B at some later time, say this one, then now VA, that is the voltage of terminal A with respect to B, is some negative voltage, let's say minus 7 volts. So over time, the voltage of terminal A with respect to terminal B keeps changing polarity. It could be negative sometimes, it was positive sometimes. And it could be of any shape. It could be a sinusoid, it could be a square wave, it could be a triangle or a sawtooth. Let's make a sawtooth. So it is not a question of what shape the waveform is, what shape the function of time is. When we say that we have an alternating voltage, we simply mean that the polarity can be both positive and negative at different times. Right. So what we want to do with a rectifier is to convert this alternating voltage into a unidirectional voltage. Ideally a constant unidirectional voltage, but at least a unidirectional voltage. The first step we take, that is just a rectifier without additional circuits, will convert a bidirectional or alternating signal into a unidirectional signal. The way we do it is using a diode. That was the reason why we studied diodes in the first part of this experiment, because a diode is inherently unidirectional. It allows currents to flow in one direction, but it completely blocks currents flowing from the opposite direction. So we use this to enforce unidirectionality, and we can do it in two ways depending upon the level of sophistication. For the experiment then, what we will do is to use a circuit containing diodes which are designed, which are so placed that unidirectionality of the output voltage results. So, coming to the actual details of the experiment. The first thing we do is to protect not the circuit but the student who's doing the experiment. And we do this by ensuring that he doesn't get an opportunity to work at the main supply voltage. So, the first thing we do is to put a transformer. This is called a transformer. It converts a high voltage, that's normally on the left side you have the mains voltage, 230 volt RMS, left side, and on the right side we have 3 terminals, and this normally can be grounded. This is called terminal A and this is called terminal B. Let us understand what's happening on the secondary side. On the primary side, you have an alternating voltage, a sinusoid, let's say this. On this side, this is electrically isolated from the other side. There is only magnetic coupling between the two sides of this transformer. So, you can choose to ground any point you like. But the main purpose of this transformer is to step down 230 volts to approximately 1/10 of that value. In fact, 1/20th of that value, so that you get around 6 volts here, minus 6 volts here, with respect to the 0. If you make this the reference, then this will have plus 12 volts, A will have plus 12 volts with respect to B. If you make A the reference, then B will have minus 12 volts with respect to A and minus 6 volts with respect to 0. to this O point. So you can use this in various ways, and we now use it in two distinctive ways. One is to build a half-wave rectifier. The half-wave rectifier is a very simple circuit that uses just one diode, and that is connected to the point A. So you have this point A, you have a diode over here, and this is the point O, and here you have a resistor. This is the load, which we will call RL. Now what happens? When A has a positive, these are both alternating voltages. The values given here are the RMS values, root mean squared values. What we do here is observe what happens in different parts of the cycle. When A goes positive with respect to O by any positive amount, this diode conducts. We can use here the ideal diode model, and so what will happen here across RL is that the voltage between OA is transferred to RL. So, while the actual voltage AO, VAO, will be this, what will appear between VA dash and O will be the following. When A dash will be equal to A, whenever A is positive, the voltage at A is positive. Whenever it goes negative, this diode acts as an open circuit. So, no current can flow through the resistor. So, the resistor's end A dash has the same voltage as O. So, what you would get here, this is VAO. VA dash O would just be this. For the positive half cycle, it copies VAO, and for the negative half cycle, it just stays at 0. Again, for the positive half cycle, it copies VAO. For the negative cycle, it goes to 0. So, the bold curve that you see in this graph is essentially the output of a half-wave rectifier. This is the circuit of a half-wave rectifier, and this is the output of the half-wave rectifier. One might argue that this half-wave rectifier is not a very clever thing, because while something is happening in the positive cycles, the circuit is just idling in the other half. That is valid, but this is not to say that power is being wasted in any way. Because you see, the resistor carries no current in the negative half cycle, and it carries the current only in the positive half cycle. So if you measure the power consumed by the resistor, it is, assuming the diode to be ideal, equal to the power being supplied from this side. No power is being wasted. However, the thing is still inefficient for a more complex reason that will become clear at a later point in this discussion. Right now, let us say that in terms of power this is not inefficient, but a better circuit can be built. What we will now do is to build the better circuit called a full wave rectifier. A full wave rectifier not only utilizes the waveform of the input side in the positive half cycle, but also uses it in the negative half cycle. How do we do that? Something very clever. Let's see what happens. So we now come to the full wave rectifier, as I was about to introduce you to it. You see, a full wave rectifier makes use of both terminals of the secondary side of the transformer, both the extreme terminals. O is of course used as the return path. So you put a diode on A, like we did before. We also put another diode on B. Now let's go over to this waveform diagram and see the waveforms VAO and VBO. in one half of the cycle, the terminal A is positive with respect to O. At that time, this diode turns on, which I will call DA, and this diode is off, and this diode I will call DB. So, at the output, across this load resistance, you will see a waveform that goes like this. What happens in the second part is that this diode stops conducting. In the second part of the cycle, the voltage of A is negative, so dA stops conducting, and so it is unable to contribute to the current in the resistance. However, at this time, the voltage of B goes positive with respect to O, and so dB starts conducting. And this conduction occurs for the second part of the cycle when A was negative but D was positive. So in the second half of one cycle, the second diode DB conducts and allows, because this sinusoid is symmetric, the same amount of current to flow through RL as dA allowed in the first half cycle. So the current through RL, which is proportional to the voltage across RL, follows this pattern that we see over here. Two identical lobes, one coming out of A, dA, the other coming out of dB. For successive cycles, for subsequent cycles, the same thing repeats. So you would again get this contributed by dA and this contributed by dB, and so on. So compare this with what the half wave rectifier gave us, which we will just draw below it. The half wave rectifier would just give you this and then idle over here. Again give you this and idle over here, as you see already in this graph. However, the full wave rectifier is busy on both half cycles. In terms of electrical efficiency, both are nearly the same. When the diode doesn't conduct, there is no energy wasted. When the diode conducts, energy is being used in RL. But there is a different sense in which a full wave rectifier is desirable in comparison to a half wave rectifier. And what is that? We now speak of having achieved unidirectionality of the output voltage. We now speak of how to make this voltage as constant as possible. Clearly, the half wave rectifier looks extremely fickle. Sometimes it produces a large voltage which is along the lines of a sinusoid. At other times it is just zero. Again it's a half sinusoid, then again zero. Not at all what we would call a constant voltage. Ideally a constant voltage should be something like this. But this is clearly not that. Not at all constant. So we would like to do something about this to make this voltage constant. That takes us to part 3 of the experiment.
So coming to the third part of the experiment, that is half wave and full wave rectification. So that we are going to done in two cases, with capacitor and without capacitor filtering. So before starting this experiment, we should take some precautionary steps before connecting the circuit. The circuit that we are going to connect will provide enough power to heat some components and burn them or even blow the fuse. So we should be extremely careful and ensure that your wiring is correct. And there should not be any loose contacts, and all the contacts should be firm. At no point in the experiment, the outputs of the transformer or the rectifier should not be short circuited. So these are the precautions that you should take. So coming to the new components in this rectifier part is the AC step-down transformer. So this red box is the step-down transformer. We will have different switches across here. This is the 230 volts. A signal will be produced with 50 Hz frequency. The output will be 12 volts. This is the one. The red wire is the in-phase component, and the black is the 12 volts out phase component. So in this configuration, the 2 points will be exactly out of phase with respect to the grounds. So these outputs are brought out to the sockets on the panel through two switches S1 and S2. So whenever you want to use this particular in-phase component or out-phase component, we should make on the particular switch. As you can see, we should just make it on. Okay. So this is step-down transform that we are going to use in rectifier case. So coming to the half-wave rectifier part, the circuit interconnections are done according to the diagram. So as you can observe in the manual, in the positive high cycle, the diode will be short circuited and the input will come across the output. And the negative half cycle, it will be 0. So the circuit can be seen along the breadboard. In this circuit, the one of the new component that we are going to see is this wire-wounded resistance. So this is also a resistance. These resistances are used mainly for the purpose of load, because we are going to get mainly the power, high power as output. So this will have high power ratings, so that the resistors will have high capacity to overcome the power. So these kind of wire-wound resistance are used. Otherwise, if you use the small resistance that we used in the previous case, those will easily blow off. So for this power, we can easily see this. So in this case, we are going to find the resistance values. The resistance values are printed on the wire-wounded resistance, and the power ratings are also given on the wire-wounded resistance easily. So there will be no any color code thing in this wire-wounded resistance. So the now input is given. Now we can observe the output. So input is given from the step-down transformer from this in-phase part. As you can see that it is directly given to this diode part. So now we can see the output across the load resistance RL 100 ohms. You can see that the rectification part is done. Easy. So this is the half-wave rectifier. So the positive cycle is same as input and negative cycle is 0. So you can observe now clearly by making variations in volts per division, times per division. So this is the half-wave rectifier part. You can easily observe input and output waveforms. You can sketch it easily. So coming to the next part, full-wave rectifier part. So the only change in this is we have to interconnect another diode. Then the input of this diode and the input of this diode is the out of phase input signal from the transformer. As you can see the interconnections. The diode is connected and the out of phase input is given to the input of the circuit. So by making switch out of phase output switch on, so we can observe the full wave rectifier output. So the negative half of the component is also made as positive. So this is the full wave rectification. So by making this, we complete this without capacitive filtering part, the half wave and full wave rectification without capacitive part.
Here is one cycle of a half wave rectifier's output. This is the time axis and this is the rectifier's output, which I will call VA-O. This is what the rectifier's output would normally look like, because in the second half cycle the diode is off and so no current, no voltage is applied and no current flows through the load resistance. So now what we propose to do is this. Let this be any rectifier, half wave or full wave, across which we have the load resistance RL. We propose to put across the resistor a capacitor. What does this capacitor do? When a non-zero voltage is applied by the rectifier to this part of the circuit, this capacitor will charge provided the capacitor voltage is less than the rectifier's output. This, for example, will happen if the initial capacitor voltage was 0. Let us suppose that at this point of time the capacitor voltage was 0. Then, as time proceeds beyond this point, there is a positive voltage being applied, the capacitor is uncharged, and with a very rapid time constant, with a very, very small time constant, because there is literally no resistance in series with the capacitor voltage will follow the supply voltage. Simultaneously, this supply, the rectifier output, is also forcing a current into the resistor. But while passing current through the resistor, the same voltage also charges the capacitor, as I said, almost instantaneously. So let's now plot the capacitor's voltage as a function of time. Now, the capacitor's voltage is literally going to follow the rectifier output until a certain point. Until this point. Now let's see what happens. After this point, if the load resistance were absent, let's just pretend for a moment that this load resistance is absent. Let's say this is not there. And let's assume that the diode is ideal. So the diode in the rectifier behind this is also ideal. So this capacitor has been now charged to what we can call Vm, the maximum, the peak voltage of the sinusoid. In the first quarter cycle, as the rectifier output voltage rises, the capacitor voltage will rise side by side with it. It will reach its peak value at this point, and after that something interesting happens. The capacitor, having been charged up to this point, and under the assumption that the load resistance has been removed, which we just made, has no means of discharging. So the voltage across these two terminals remains at the peak value because the capacitor has been charged and has no way to discharge. Now, let's look at the diode that ought to be here. In the case of, say, a half-wave rectifier or a full-wave rectifier, doesn't matter. Now, this diode, in the absence of this capacitor, would have continued to conduct until the 180 degree point of the sinusoid. But because of this capacitor, this diode is now faced with a falling voltage on the rear end. On the anode end, the voltage is now falling, but on the cathode end of the diode, the voltage is fixed at the peak value that it just crossed. In short, the diode stops conducting at this point itself. At this point itself, the diode stops conducting. Because after this, the anode voltage becomes lower than the cathode voltage. The cathode voltage is being maintained by the capacitor because it is now present. Whereas the anode voltage has started falling. So the diode has got reverse biased at this instant rather than at this instant as was earlier the case. So essentially, the diode has only conducted in a quarter cycle. And after that, the diode does not conduct. The output under ideal conditions, when there is no resistor and when the diode resistance reverse resistance is infinity, would follow this up to this point and then would remain flat. Whereas the input to the rectifier has gone down, gone negative, gone up again, gone positive again. This just remains flat forever and ever under ideal conditions. However, if we have any kind of resistance across which the capacitor can discharge, then a very different thing happens. If there is any scope for the capacitor to discharge, such as by having a load resistance, let's reintroduce it over here. Then between, or rather after this point, the capacitor does indeed begin to discharge, and instead of its voltage remaining constant for the rest of the future, it starts drooping. How long does it continue to fall? It continues to fall until the time when the rectifier input side produces a voltage which exceeds its voltage at that point of time. So you have an exponential curve going down at this point, and you have a sinusoidal curve going up. And at the point, at that instant of time when the rectifier input voltage exceeds the capacitor output voltage, this capacitor now starts charging once again, because the diode is again forward biased, because its cathode end is a lower voltage than the anode end, so it starts charging once again. It charges up to this point, but again turns the diode off, because now the capacitor is charged up to here, and the rectifier input voltage starts falling. So this repeats. In the second cycle, again the capacitor voltage droops because it discharges through the load resistance, and you get this. Again at this point, the rectifier input voltage exceeds the capacitor's voltage, and so the diode gets forward biased and it charges the capacitor. So finally, with the capacitor present, unlike the case when the capacitor wasn't present, you have a voltage which is periodic and which has this sort of a shape. Let's ignore this part because we really believe this was the first cycle. In the steady state, there is no first cycle. This thing is just continuously repeating itself. So you would have something coming like this, and then going up, and then discharging, and again charging, and then discharging, and again charging. This is the capacitor's voltage, or VA'. Compare this with what you would have got in the absence of the capacitor. You would have got this flat, this flat, this. This is what you would have got. Certainly a big improvement, because the peak to peak variation of the output voltage is only between these two extremities, whereas earlier it was from here to here. Clearly, if you want to reduce further the peak to peak range of the output voltage, either you have to increase the load resistance, which is not something that you would want to restrict. You would like the load to be whatever it wants to be. So what you would do is put a larger capacitance. And when you put a larger capacitance, it would discharge more slowly because it has more charge capacity. And so you might get a waveform that looks like this. And it would also be here, like this. So depending upon how large the capacitor is, it gets less and less wavy, more and more constant. At this stage, it is worthwhile to understand the advantage gained by using a full wave rectifier against a half wave rectifier. You see, the amount of peak to peak variation, I just said that this amount of variation depends upon R and C, or on the product of R and C, which is not incorrect. But it also depends on another thing. It depends upon the distance between the two times at which the capacitor gets an opportunity to charge. And in the case of a half wave rectifier, those two times are one cycle, one period apart. With a 50 Hz supply, that means this point and this point are 20 milliseconds apart. Whereas, if you used a full wave rectifier, they would only be 10 milliseconds apart, because at the very next half cycle, instead of the next alternate half cycle, you would again get an opportunity to charge the capacitor. Let's look at what happens if you had a full wave rectifier. Now the capacitor would only discharge by this much instead of this much. So instead of this much, you have only this much. And again, it would charge up to here and only discharge by this much. Charge up to here, only discharge by this much. A far more level waveform than what you would get with the same capacitor, same resistor, if you had a half wave rectifier. A full wave rectifier is giving you a far more constant output, an output with much less time variation. So clearly a full wave rectifier scores over a half wave rectifier in this respect, and that's why we use a full wave rectifier. This is the circuit you use to observe the waveforms of the output of a capacitively filtered rectifier. What you have here is the filtering capacitor and the load resistance. Here I have just said rectifier out. It could be a full wave rectifier or a half wave rectifier. Indeed, you have to carry out the experiment with both these. And we also include a small series resistor of 1 ohm on the ground side of the load resistance. That means to say, we don't ground this point as we were grounding earlier, but we ground this point. The series resistance is required to make current measurements. It is very interesting, and we will come to this in a moment, that the current flows for a very small minuscule point, minuscule portion of the cycle. And the current doesn't just flow through the resistor, it flows through the capacitor as well. So the current that actually flows through Rs is the net current taken by this entire portion of the circuit. And that is what will be of interest to us to understand. The last time we were trying to measure current, which was when we were trying to plot the diode characteristics, we put the series resistance meant for voltage measurement on the source side, not on the ground side. And therefore, measuring the current by using the proportionate voltage developed across the resistor required a difference amplifier. Here we don't need to do that, because one end of Rs is already at ground, so channel 2 that's connected to this will directly give you the voltage across Rs with respect to the ground, and that voltage will be proportional to the current that's passing through. What, however, is happening is that the voltage that is measured by channel 1 is not really the voltage across RL. It is the voltage across RL plus Rs, and that is not accurately the output voltage. It is therefore it would have been ideal to put a difference amplifier between these 2 points and set that to channel 1. We don't require to do it here, because this being a very small resistance, the voltage, which is the sum of these and this voltage, would literally be equal to this voltage, because this is very, very small. Hence, we are going to use the channel 1 output as an approximate measure of the load resistance voltage, or the output voltage of the rectified filtered system, to tell us how it works. So now you see what happens. This channel 1 voltage will essentially tell us how constant the voltage is. This we already plotted for a sinusoid, for a full wave rectifier, for example. We would get an output voltage that goes something like this. This would be VO, the output voltage. This is what it would look like. Now, to understand when current will pass through Rs, we have to look very carefully. It is only from this instant of time until this instant of time that the diode is forward biased. Rest of the time the diode is reverse biased. Again, in the next half cycle, it is only from here until here that the diode is forward biased. Rest of the time it's reverse biased. Let me make this a little more straight. Again, here the same thing. Here and here. Here and here. So it's only when the diode is forward biased that it can conduct current. And if it is the diode current that's coming in here, it is the diode current that's going out here. The resistor itself will carry current for a longer period of time, but that current is being sourced by the capacitor, not to be measured through Rs, because Rs is outside the resistor capacitor pair. So this pair consisting of resistor capacitor only allows a current to flow in for these short intervals of time, and during these short intervals of time a current will flow that is approximately proportional to the voltage. So the current waveform would look like this. This is what the current waveform looks like. The diode current waveform. Sorry. The diode current waveform would look like this. The diode indeed has to pass a reasonably large amount of current to maintain even a moderate amount of current in the load resistor for the entire cycle. Because all the current that flows through the resistor over the load resistor over the entire cycle has to be supplied in terms of an equivalent amount of charge over a very, very small fraction of that interval. And that fraction gets smaller and smaller as the capacitance gets larger and larger. So for a very large capacitance, when the diode gets forward biased, it literally is short circuited to the ground. Almost short circuited to the ground, except for Rs and some internal resistances of the diode. So the larger the capacitor you put, the stronger is the current pulse, the higher is the amplitude of the current pulse, and this is a caution to us that putting on a very large capacitor would give you a very level waveform, but it takes you to the risk of blowing up the diode by excessive current, by excessive forward current in the diode. So this more or less completes whatever we wanted to say about this experiment. You should be able to observe this current, this waveform on channel 2, this waveform on channel 1. End of story.
So, coming to the rectified part with capacitive filter, in this section we will study the effect of capacitive filters on ripple voltage and peak diode current. The 1 ohm resistor in the following circuits is used to observe the diode current waveforms. By using one channel of the Esc2 to observe the output voltage and other channel to observe the diode current simultaneously, we have two channels, channel 1 and channel 2. So, the circuit connection is done according to the diagram that is given in the manual. So, this is the half-wave rectifier output that we are going to observe in the DSO. So, these are the ripples that we are going to observe because of the capacitor part here. In this part, in the positive cycle, the capacitor starts charging. So, in the next negative half cycle, it is discharging. So before completely discharging, again the positive half cycle will come and it will start again. So it will again start starting. So that's why you will observe these ripples. So the next part is the capacitor. Coming to the second information, the capacitor that we are going to hear is electrolytic capacitor with 330 microfarads. So we can observe the output waveforms here. And we can also measure the peak to peak ripple voltage easily. With the ripple, we can measure the peak to peak ripple voltages. So the other thing that we have to find is the diode current waveforms by using channel interconnections. So these are the waveforms. So this is the diode current waveform, and we can find the peak value of the diode current easily from the given diagram, from the diagram observed in the DSP. So coming to the full wave rectified part with capacitive filtering, the circuit connection is done according to the diagram that is given in the manual. So by making on the out of phase, we can see the full wave rectifier with capacitive filtering output. So here the peak to peak ripple voltage has been reduced because in both the positive half cycle and negative cycle we will have only positive component, so capacitive charges in both the phases. And the next step we have to repeat the steps that we have done previously. In this case we have to observe at different capacitor values, that is C is equal to 100 microfarads and C is equal to 330 microfarads and 1000 microfarads. So we should find the peak to peak ripple voltage and peak values of the diode current in each and every particular phase. So we can easily change the capacitors from 330 volts to 100. So while making changes, please be careful the positive and negative terminals of the capacitor. If you interconnect in reverse way, the capacitor might go away, it will blow off. As you can observe the full wave rectification by using capacitive part, filtering part. So that is the 330 microfarad capacity that we have kept here. So by measuring the peak to peak, you can easily measure the peak to peak voltage and the diode current. So the final part that we have to do is we will compare the peak to peak ripple voltage and the peak value of the diode current for both half wave and full wave rectification. Both half wave and full wave rectification. And that we have to do with the 330 microfarad capacitor part. So we can compare easily by making of the out of phase button off. So this is half wave rectifier, and you can measure the peak to peak voltage and the diode current. And by making it on, we can easily find the peak to peak voltage of full wave rectification part and the diode current. So we can compare both these voltages and currents, and we can easily verify which is greater and which is not. By doing this, the half wave rectification and full wave rectification with capacitive filtering part is done. By doing this, the experiment has been completed. Thank you.